Let's discuss mutual induction. These are two coils wound on a common core. Say the core is a wooden cylinder. Let's show these coils as C1 and C2. These lines represent the common core. A battery is connected across coil C1 through a tapping key, and a galvanometer is connected across coil C2. Now, if we press this key, current in C1 will increase from 0 to maximum. So, magnetic flux linked with C1 will increase from 0 to maximum. Because C2 is in neighborhood of C1, so magnetic flux linked with C2 also increase from 0 to maximum. Magnetic flux is increasing. There is a change in magnetic flux. So, an EMF develops, an induced EMF is developed in coil C2, and an induced current flows through C2 in this direction, in the direction opposite to cell current, so as to decrease the magnetic flux or to decrease the current. Now, if we release this key, current in C1 will decrease from maximum to 0. Magnetic flux linked with C1 will decrease from maximum to 0. Also, magnetic flux linked with C2 will decrease from maximum to 0. Magnetic flux is decreasing. Change in magnetic flux. Again, an EMF, induced EMF develops in C2, and an induced current flows, but now in opposite direction. In this direction, in the direction of cell current, so as to increase the current, so as to increase the magnetic flux. This is in accordance with Lenz's law. Means both time, in both cases, when we make the circuit or when we break the circuit, in both the cases, induced EMF develops in C2 and induced current flows. How to remember the direction of induced current? When the battery current is increasing, direction of induced current is inverse, opposite to battery current. In this direction, increasing, inverse. And when the battery current is decreasing, the direction of induced current is in the direction of battery current, direct. So in this way you can remember the direction of induced current. We have seen that in both cases, either when the current is increasing or when the current is decreasing, in both the cases induced EMF develops in coil C2 and an induced current flows through C2. It means a varying current in a coil can induce EMF in the neighboring coil. This phenomenon is called mutual induction. That is, varying current in a coil can induce EMF in the neighboring coil. Means for mutual induction, current must vary in the circuit. Let's calculate the induced EMF. In coil C2, let a current I1 flows through coil C1. And let's calculate total magnetic flux linked with C2 due to this current I1. Let phi 2 is the magnetic flux linked with one turn of C2, and if there are N2 turns in C2, then total magnetic flux linked with C2 will become N2 phi 2. And it is found that this magnetic flux depends upon I1. It is directly proportional to I1. Removing this proportionately sign, we introduce a constant which is mutual inductance of coil C2 with respect to coil C1, M21 into I1. Now, if this current I1 is varying, it is changing, then we can find out d by dt of d by dt of n to phi 2, rate of change of magnetic flux linked with C2, because when this current is changing, magnetic flux linked with C2 will change. So rate of change of magnetic flux linked with C2 equal to M21 into rate of change of current through C1. What is this rate of change of magnetic flux? It is induced EMF with minus sign. Let's call it E2 because we are talking about induced EMF in C2. And this is equal to M21 into di1 by dt. Negative sign tells the direction of induced current. This is in accordance with Lenz's law. Or we can write E2 equal to into di1 by dt. Now let's consider the reverse case. Let's connect a battery across C2 and a galvanometer across C1. Let a current I2 flows through coil C2. Let's calculate total magnetic flux linked with C1 due to this current I2. Let phi 1 is the magnetic flux linked with one turn of C1. And if there are N1 turns in C1, so total magnetic flux linked with C1 will become N1 into phi 1. And it will depend upon current I2. It is directly proportional to I2. Removing this proportionality sign, we introduce a constant which is mutual inductance of coil C1 with respect to coil C2, or we call it coefficient of mutual induction of C1 with respect to C2 into I2. Now if the current in C2 is changing, it is varying, then there will be change in magnetic flux in C1. So we can find out rate of change of magnetic flux linked with C1 d by dt of N1 phi 1. This must be equal to M12 into d by dt of I2. Now, what is this rate of change of magnetic flux? It is induced EMF. Because it is in C1, so let's call it E1. This is equal to, or we can write it like this. In previous video, when we calculate mutual inductance of two long coaxial solenoids, we proved there that M12 is equal to M21. This is equal to M. Now this equation will become M into di2 by dt. M is called the mutual inductance of two circuits or two coils. E1 is equal to this. And the previous equation, this will become M into, instead of M21, we can write M into di1 over dt. So in general, we can write E equal to M into di by dt, where E is the induced EMF in a coil and I is the current through the neighboring coil. From here we can define M. Well, M will be equal to E, or E will be equal to M if di by dt equal to 1. So E will become equal to M. So we can define from here coefficient of mutual inductance, mutual induction of two circuits. So mutual inductance or coefficient of mutual induction of two circuits is equal to induced EMF developed in one circuit due to unit rate of change of current through the neighboring circuit. Or we can say mutual inductance of two coils is numerically equal to EMF induced in one coil due to unit rate of change of current through the other coil here neighboring coil. Let's now talk about the practical unit of mutual inductance. It is Henry. Let's define 1 Henry. Now here M will become 1 Henry. When will it become 1 Henry? When this is 1 and this is 1. In that case, E is equal to 1 volt when di by dt is equal to 1 ampere per second. So we can say that mutual inductance of two circuits will be 1 Henry when current changing in one circuit at the rate of 1 ampere per second produces an induced EMF of 1 volt in the other.